Okay, so welcome back to lecture. I hope everyone had a good spring break. We are at the point where we need to have an exam. We've covered logic. We spent a lot of time on logic, proofs, and then we have set theory and functions. So these will be all the topics that will be covered on the first exam, which will be this weekend. I'll write up a document for you guys. I'll post it on Blackboard. You print it out. You will have probably, I'll give you like 5 hours. And you just have to sign your name saying that you followed the instructions. Right? Like you spent your start time, your end time. I'm letting you use the textbook as like open notes, I suppose. And I wouldn't stress about it too much. And you'll turn it in. So you'll have to come in, all you Zoom people, you'll have to come in and turn it in next week. If you're on campus and you can't make it to the actual time of the class, you can slide the exam under my door. And I think because some people might be busy this weekend, you can turn it in Wednesday. So just don't, like if you're gonna start it, you have to start it. So don't look at it unless you're ready to go and you print it out. Like you can print it out, but like don't flip through it. I'm just trusting you on that. Okay. So with that being said, in today's lecture, we're going to go over example problems that might be on the exam, things similar. And for reference, just so you know, this is the book that I'm using to write the exam. Okay, it's that Rosen textbook. There's a PDF of it online. You don't have to buy it, but this is what I use for my notes and when I write the exam. Okay. So with that being said, let's go ahead and get started. So maybe I'll look at something like, let's start with logic, right? There's going to be questions on logic. It's been a while. Maybe we should like have a refresher. So like problem 1. So I tend to like things like this. So show, let's say, if P then Q, and if Q then R, P then Q and Q then R, implies if P then R, show this as a tautology. Okay. So there are lots of implications. Maybe there's 3 of them. There's an and, there's 4 of them, there's an and so what is this like? What is this problem saying? It's like, well, we have this compound proposition, and we want to show that it's always true. That's what a tautology is, right? So the way that we can do that is by, well, there's a few ways, but referencing the tables in that section in Rosen that I've shown you, like referencing those tables, we should be able to logically string together those equivalences to get this is a capital T. Okay, so when you see a problem and you write it on your exam, you should definitely write it exactly as I write the solution, right? Like right underneath the problem, you'll have white space, and then this is a proof type problem, so there's going to be a PF right there, indicate you're going to write a proof, right? So there's one condition that like I use all the time when doing these. I call it star. So like somewhere, like you'll have that if P then Q is logically equivalent to not P or Q. And I call this star. So if you use that thing, just call it star, by star. You really don't need many of those things in that table, right? You need that one, and then like the associative law, the distributive law, double negation law, these types of things. So let's see if we can get there. Now, All right, so writing the solution out, I'm going to rewrite this guy. It's kind of long. And you can go ahead and maybe write underneath it. That's logically equivalent to something. Okay. So my suggestion, whenever encountering these things, and you have conditional statements like if P then Q, if Q then R, get rid of all of those things by using star. Right? Once you transform those into an or, then you can start using associativity. You can maybe use De Morgan's law somewhere, things like that. So I'm going to get rid of this first one right here. So like this is the hypothesis, right? That's the conclusion. So we know the conditional is logically equivalent to not the hypothesis or the conclusion by star. So realistically, we could apply it to each one of these. We could. So I would allow it. So this is logically equivalent to not this thing. Just to be very careful, I'm not going to do that right now. And I'm not just saying that like I haven't solved this problem, I don't think, before, so I'm being very careful. It's really easy to make mistakes. So that negate that hypothesis or the conclusion. And because you want to be as clear as possible when writing your solutions, by star. Okay. So next up, maybe we can apply star again to these other little pieces here, right? Again, we could have realistically done it all at once, but I'm being especially cautious because I don't think I've done this one before, and I don't want to make a silly mistake. So, okay, I'm going to leave that negation out there, and I'm going to change that one to not P or Q, and not Q or R. Or not P or R. And again, this is by star. And then if you wanted to be like especially clear, by star like 3 times. So you can see that there to there, there to there, there to there. Now, you really should try your best to write the next line underneath that, next line underneath that, next line underneath that. I ran out of room here, but that's when you're writing your solution, stack them. Okay. Okay. So now, the only law that I really see that I could use right now, I see the negation of something and something else. De Morgan's law. Okay. De Morgan's law applies in that case. So I'm going to apply De Morgan's law right here. Send that negation in. So then this will be logically equivalent to not P or Q, or negation of not Q or R, or this part here, not P or R. And this would be by De Morgan. Okay. So then I see the negation of something or something, negation of something or something. I can apply De Morgan's law again. So then we have not, I'm going to use brackets now. You'll see why in a second. The negation of not P, like that, and not Q, or negation of not Q, this would be an and, not R, or negation of P or R. Let's try them working. Again. Right? All I did was send that negation in there, comes that, send that negation in there, it's that. Now, I see double negation happening there. Double negational, negation of not P is just P. Okay? So things are starting to collapse. So this would be P and not Q, or Q and not R, or not P or R. Okay, and we're hoping somehow to land at a capital T somewhere, right? Now it looks messy right now. However, maybe we can work with it.
It's not our division. But our advisor.
So the only option we have is to use the distributive law, maybe. And like, I see there's a Q there and there's a Q there, right? So maybe if I can send this whole thing in there, maybe that Q and not Q will like go away somehow. So, oh, I almost forgot. I should have reminded me. That line was by double negation. So I'm going to distribute that into this thing. So you were treating this as its own thing, right? And it's distributed because we have an or and then an and. And so I don't have enough room to remind you what the distributive law is, but it's like that or that, right? And that or that. So it's going to be long, but we'll see. So we have P and not Q, or Q, like that. And P and not Q, or not R. So that's distributing this into that. And then the other thing stays the same, or not P or R. And that was by distributive law. It looks messy, but we'll see what happens. Again, you have to be prepared to go down a route with these. So then here, I'm going to focus in on this piece right here and distribute in. Okay, so, all right. There's actually an easier way to do this, I just realized, but it's easier but sophisticated at the same time. But we're just trying to string together these logical equalities right now. Okay, so here, I'm going to distribute that Q into here. So that or that, and that or that. So this would be like P or Q, and not Q or Q. And then the rest, I can stay the same. P. Admittedly, this one is a little bit longer than what I would put on the exam. I just picked it at random. But there will be one in the exam that's like this. This one might be a bad illustration because of how long it is, but there will be a question like this. Okay, so now there are some things that are about to happen. This right here, not Q or Q, that's true, right? At least one of those is true and the or is true. And then we'll have that and true, which is equivalent to that, right? So really this line becomes P or Q. And this stuff here. Now I did some things here. This is going to be true. I think that's, what is that called? That's a law. It's called negation law. So this is going to be true by negation law, and then that and true is just that by the idempotent law, I'm pretty sure. No, identity law. So you would write out by, what is it? Negation and identity. Lots of tedious business going on. Again, this one's longer than the one that you'll see on the exam. I'm just going to illustrate or reminding you about these logical identities. So what's going on here? I really think that I should maybe distribute in here, right? Here. Yeah, that seems like the thing to do. I probably should have picked a better problem. So this will become that or that and that or that. So let's write that out. P or not R and not Q or not R, or not P. Be very careful there. Now it's by distributable. Okay, so we've made it here. And do we see anything that can help us at all? I'd like to make this thing go away quickly. It's taking too long. So, okay, looking at it. Let's make sure that like the steps are correct, right? I'm starting to get a little bit concerned that I might have made a mistake because it's taking a lot longer than I thought. So let's look through the steps and check ourselves, which by the way, you can do as well, right? Like if you've written down each of the things you've done, right? Then you should be okay. You can check it. So original statement to there, not that or that. Correct. Not that or that, not that or that, not that or that. 3 times, check. And then here, send in the negation by De Morgan's law. So the not that or not that or not that. Okay. By De Morgan. Up to here, we're good, right? So then we send in the negations again. So not that and not that, good. Not that and not that, good. Didn't do anything there by De Morgan, fine, right? So you see why it's important to write this, right? Not only for me when I'm grading it, but for you to like check yourself and know whether or not you're on the right track. So then double negation, bam, double negation there, and then we're good. Okay. So far so good. Now, I'm kind of curious now, looking at that, if I made the right choice to distribute in there. It did collapse a little bit, but it's not going quickly enough. Like it's still 4 things long, right? So, and my board is too small. Do you think that we're getting close? What is your opinion? And can you see, like, can you imagine, this is a part of like problem solving, can you imagine that the solution is coming up? Like that we're making progress. So at this point, I don't know if I'm making progress, right?
Feels like we're just going in circles.
Right, and that happens with these, right? So looking back at my table, I'm looking at the table right now. P implies, so there's 1, so P implies Q, right? And then Q implies R. Q plus Q, Q plus R. So I'm looking at the table. I don't see anything to help me there, actually. Looking, because right now I'm using like the bare minimum rules. I've just used star and De Morgan's and distributive, right? But there's a whole table right there. And if I can't find one that's going to make this go quicker, I'm going to show you another way to show that tautology. So let's see. P or, so right up there. I don't see one. It's really going to make it go quicker right now. Because I want to collapse things down. So I'm confident that if we kept on going, we'd get it, but I don't want to take too much time on this. There's a different way to do this. So, okay. We can prove this using the proof techniques that we know about. And I think it's probably a good idea to do that to save time. I'm annoyed because I want to finish this, but the other way will work. All right. So we have a conditional statement, right? And we want to show that it's a tautology. So one thing that we can possibly do, maybe, is suppose that it's false. What did we learn about proof techniques? There's 3. There's direct proof, contrapositive, and contradiction, right? So maybe we assume that this is false and we get a contradiction. It's a conditional statement, if that, then that, right? So maybe, right? This is like my favorite proof technique to throw at things, right? Contradiction. I've mentioned that in lecture. Like, if I want, the first thing I'm going to try is contradiction to get an idea. It gives me the most information. So, by way of contradiction, I bet you this is going to work out well. I don't want to get too ahead of myself, but let's see. So, by way of contradiction, suppose that if P then Q and if Q then R implies if P then R, suppose that's false. Right? Suppose that's false. Now, this is actually very useful. I don't know if you see it, But what's the only time the conditional statement is false? There's only one time that happens. When the something is something and the other thing is something. There's only one time when the conditional is false. Right, when the hypothesis is true and that's false, right? So we get information to work with. So then, by definition, if P, then Q, and if Q, then R must be true, right? And if P, then R must be false, right? I hope that's clear. The conditional statement is only false when the hypothesis is true. So like this is the hypothesis, and this is the conclusion, right? So it's only false when that's true and that's false, right? So under this assumption, it must be the case that that is true, that's false. Clear, maybe? But then we have all sorts of things to work with, right? This is only false when something has to happen, right? This is only true when both of those are true, right? We're getting information to work with. Do you see where I'm going with this? And by the way, I know that this has been an extended example, but this is actually fun. Like if you think about it in terms of like problem solving, we're trying to figure out the answer, right? And if on an exam you string together a bunch of logical equivalencies and you get stuck, you can try another way. But if you keep your logical equivalencies on there, you can still look at them and maybe figure it out. So we can work with definitions now. So I would write right here, but I'm running out of room. I'd say, by definition again, so this is true, which means that's true and that's true, right? So if P, then Q must be true. If Q, then R must be true. And this is only false when that's true, and that's false, right? So we know that P must be true, and R must be false. We have a bunch of information, right? I feel like I'm getting somewhere. And again, we're doing this by contradiction, so we're hoping to find a problem, like something is both true and false at the same time. So because we know the value of P and because we know the value of R, we can just plug in there and there, right? So hence, maybe, we have true. So I'm looking at this guy. P implies Q. I'm replacing P by what it is. It must be true, right? Right? I take that and I put it in there. And then I take that R and I put it in there. Oh, I think we got it, maybe. So R is false. Right, so R is false. Look at that, we're almost there. So what does this imply that Q must be for this to be true?
Has to be true.
Q must be true. But what about there? If Q is true,
It has to be false.
we found it. We found the problem. And again, maybe. So Q must be true right there. And Q must be false from there. A contradiction. We're done. and then put your stamp. We found it, right? We see that there's a problem that has to happen. Again, let's like reiterate this. We suppose this conditional is false, which means that's true and that's false. That's that first sentence. But then if that's the case, that's an and, right? That has to be true and false, right? So we get true, 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 false immediately. And then we just plug back in and we get that, oh, Q must be true from this one and Q must be false from this one. These two things happen at the same time. Propositions are either true or false, never both. That's a problem. Contradiction, we're done. Long-winded, but I think a valuable example, actually. So we got stuck using you can think of stringing together the logical equivalences in the table is like very procedural. But that's not really what mathematics is in general. Like problem solving in mathematics is really more about trying ideas and using like reasoning, right? Stringing together equivalencies, there's not much reasoning. You're trying to find the ones that fit. Here, we actually use reasoning. We use the technique that we learned. Contradiction technique. We assume the negation of this, which means that it's false sometimes. Under that assumption, we get all of this information that leads to a story. And we actually can say more now, right? Think about it. Like it would be difficult, right? But we can explain why this is tautology. Because if we assume it's not, then it's false sometimes. And then under that condition, we know that this is true and that's false, which means that all of these values have to have these values, which means that you get that Q must be true and false at the same time. With the logical equivalencies that we would have strung together, did you understand anything? Like it wasn't telling us a story. This tells us a story in a sense. Okay, so you'll have one like this. It won't be as long. I already know the one I'm going to give you. But you can prove it with logical identities. Actually, not that bad. It's probably like 6 lines. Or you can do it this way. Either way will work. Okay, so that actually was a good example because we ended up talking about a proof technique, not just equivalencies. We reminded ourselves of the definitions. I'm not bummed about it. Okay, so next problem. Okay. Let's see. I want a good one. Well, we're going to continue our review next time, by the way, as well. So for the sake of time, I'm going to skip to the little basic number theory proofs. There'll be 2 of those, like odd and even things or rational things. Okay, so let's go ahead and do one. So yeah, this will be like something like this, like show the square of an even number is even. That's another proof one. We can do this directly, right? Now, when we were covering proofs, I asked you to split the paper in half, have your scratch work and your real proof. I think that would be a good idea to do when you write your solution. So I can like kind of sift through your scratch work and give you like partial points if you don't get it correct. Like, kind of go through it. Now, I'm not going to do that when I give this solution here, but it wouldn't hurt for you to do it to help me give you points. Like I don't want any of you to do bad on the exam. I search for points. So put your scratch work on the side when you write these types of proofs. Okay, so at least for yourselves, you might want to rewrite it, like not in your solution, but for yourselves, rewrite this as what it is, as a conditional statement. Right, so I'll write it for you in blue maybe. You wouldn't do this on your solution, but in your notes, when you're working on the problems, it might help. So this is equivalent to saying, for all n that are integers, n is even implies n squared is even. And there will be a question on the exam that actually does something similar to this, where I give you like maybe 4 parts to one question, where I have like worded statements and I ask you to write them using quantifiers. Right? All right, so let's go ahead and look at the proof. Again, this should be like directly underneath the thing. Right? So this is a direct proof you could do this with. You tried the other techniques, it wouldn't work to your benefit. So we can start this by saying, suppose n is an even integer. Suppose n is an even integer. And then if you remember, there's like a step-by-step process to this. You make your supposition and then you recall the definition. So then by definition, there exists some integer k, like that maybe, such that n is equal to 2 times k. Okay, so then next step is a little bit of algebra. So you can say like hence n squared is equal to 2k all squared, like that. Notice my placement of the equation. Yeah. Now this doesn't look even to me, but we can make it look even, right? Definition of being even is twice an integer. So I just factor out a 2. Like that. And then we just have to restate the definition, emphasizing that's an integer, right? So since two k squared is an integer, n squared is even by definition. QED. Done. So there'll be like two of like these simpler types of like number theory proofs, probably. I don't like long exams because I don't like grading long exams. So there'll be like 10 questions. Okay, so I'm gonna do like one more problem, but next time I'll do another one of these as well. Right, so you'll have plenty of review and all these will be on YouTube so you can watch. Okay. So okay, maybe this one. Okay, so next up, show A intersect B minus A is the empty set. Hopefully you watched my set theory videos on YouTube. So I'm assuming that you're familiar with the definitions here. Okay. Now, we can do this a few different ways. There are tables of set identities, just like logical identities, but then we could also do it with the proofy way, right? Because this seems kind of like obvious that if you assume that that's not empty, then there has to be something in there and in there. But then there should be a problem like immediately. But you could use these identities. They are in here. So I don't know. And honestly, to me, it just seems easier to do contradiction again. Because you'll see what I mean. And let's just do it. I'm hoping that all of you know how to will maintain a lot of these proofy things after this course. So more you see, better, whatever. So I'm going to assume by contradiction that that's not empty. So by way of contradiction, suppose A intersect B minus A is not empty. And the empty set is a set with no elements, so we're assuming it's not empty, which means that there's at least one element in that set, right? So you can say that. Then there exists an X that is in there. We're assuming that it's not empty. Right? And this is the intersection, right? The intersection is like the set equivalent of the the conjunction between propositions, right? So I'm going to say by definition now. So by definition, X is in A, and yeah, I can use that. I can do and X is in B minus A. Okay. And we know we can even like write out that this is like equal to logically equal to true, because that's a logical statement, right? So if we're assuming that, then this must be true. Okay. This is really not picking up on the recording as well as it should. Now the definition of the set difference, right? B minus A, right? That means that B is in A and B is, sorry, it means that X is in B and X is not in A, right? So we can say something like, since, well, maybe just say like hence, or by definition again. By definition again. We convert that to what it is. I'll just write it in the middle. X is in A, and X is in B, and X is not in A. Right, that from there to here. That's the definition of the set complement. And then we can like group these together, right? We have a bunch of ands, we have associativity and commutativity properties. So then like underneath this one, so to indicate, I would do like an arrow like that. This is the same, this next one. That. And X to B. All that has to be true. And this is a contradiction because of that right there. That's false. Can't be an A and not an A. You see that? Yeah.
Could we prove these questions like this using Venn diagrams?
No, you could get an idea about how to prove it, but it wouldn't be general because there's so many different ways that like you can draw these combinations of things, right? You'd have to like enumerate them, right? Or like, what if B is empty? What if there's nothing in B? Okay, or what if A is empty, right? But again, like if you follow, like if you watch this recording and you match it up with the problem that you might see, you can like literally follow it and it should be roughly the same. Okay, so this is a contradiction. Or actually, I can write it even. I can write one more line here. This. That's false, right? You can't be in there and not in there at the same time. But then this is the conjunction operator right here. False and anything is false. There's the contradiction. Now, this was like a worded proof for it. You could possibly look at this a little bit different with like maybe like another way of proving this would be like this. Note B minus A as the set of all x such that x is in B and x is not in A, right? That's just the definition, right? But this is equivalent to set of all x such that x is in B and x is in A complement. Your side book might put a little C right there. It's the same thing, complement. If x is not in A, it's in the complement of A. And now we have the and, which is the intersection. So this is B intersect A complement. So B minus A is the same thing as B intersect A complement. So then if we look at the original thing, we have then A intersect B minus A is equal to A intersect B intersect A complement, like that. Because that's that and that. And then we can group these together by by the commutative laws. So we can then have A intersect A complement intersect B by commutative laws. And then A intersect A complement, I think that's a law. It's a complement law. So empty set intersect B by complement law. And then empty set intersect anything is the empty set. That's by the domination law. Domination law. So then that's equal to the empty set. So there's just two different ways of doing it. There's the worded way with contradiction, and there's also noticing that B minus A is equal to B intersect A complement. And if you plug that in, you can apply the laws in that table and get that, oh, it is the empty set. Okay. There's two different ways of doing it. So this was probably like, this will conclude like today's lecture, which was heavily focused on like the argumentation and the proof stuff. In next lecture, we'll look at more of like the more computational-esque type problems that you might be asked. We have to like calculate things. Right, so this is the proof side, and then calculation is next time. All right, so that'll be it for today's recording.